Now let's look at the property which governs how we multiply radicals. First off, we have the nth root of a times the nth root of b is equal to the nth root of ab. That tells us, first off, we need to have the same index when you multiply radicals, just as when you add radicals. However, you do not have to have the same radicand. Basically, you are going to multiply the radicands together, and that will give you what is inside the radicand of the combined or product. Let's multiply these together. In this first problem, the square root of 3 times the square root of 2, they're both square roots. We multiply the radicands together and we get the square root of 6. For problem number 2, we see that we have square roots again. The 5 and the 7 are on the outside, so we multiply them separately, and then we do the inside of the radicands to get times that should be times the square root of 22. For number 3, these are both cube roots. The outer coefficients, 5 times 3 is 15, and inside the cube root we have 7 times 2, which is 14. For number 5, both of these are fourth roots, so outside 2 times 4 is equal to 8. Then we have the fourth root of 3 times 27 is 81. X to the 1 plus 6 is 7. Now 81 we know is 9 times 9, which is 3 times 3 times 3 times 3. And we're looking for a 4 of a kind because we're taking the fourth root. So that 3 is going to come outside and multiply with that 8 and give us 24. With the x to the 7th, we can go 7 divided by 4 is 1 remainder 3. So we have 1x on the outside of this fourth root and x to the 3rd inside. Now, technically, we took a fourth root and our answer must be positive. So there will be absolute values around the x unless there are directions that tell us that the variables only represent positive integers or positive values. This next problem is a FOIL problem. We have a binomial times a binomial, and we're going to do all this distribution. Be very careful when you do this. 8 root 7 times root 7 is 8 root 49. Don't try and do it all in your head. On the outer, we have 8 root 7 times 3 root 5, and that will give us plus 24 root 35. On the inner part, we're going to have minus 1 root 35. And on the last part of FOIL, negative 1 times positive 3 makes negative 3 root 25. Only now will I simplify these radicals. I've really got an 8 times 7 here at the beginning, which is 56. These middle terms can be combined together. I've got a negative 3 times a 5 at the end, which is negative 15. So combining the 56 and the negative 15, I have 41, and then in the center I will have plus 23 root 35, and that would be the answer to this problem. On this next problem, which is a binomial square, do not square across that minus sign. Instead, write this as 6 minus root 11 times again 6 minus root 11. The first part of FOIL gives us 36, and we're going to have a minus 6 root 11 and again a minus 6 root 11 for the interior terms, plus 11 squared, or square root of 11 times the square root of 11, which is just going to be 11 here. Combining the outer and the inner terms together, we have 47 minus 12 root 11. This is where things start to get kind of fun. We have a square root times a fourth root, and those cannot be multiplied together as it's currently given to us. But we have the power of fractional or rational exponents to work with here. So if we rewrite this as x to the 1/2 times x to the 1/4, now this becomes something we can work with. We know that we can add exponents when we're multiplying common bases together, and to add these we're going to need a common denominator in those exponents. So we will have x to the 2/4 times x to the 1/4, which you know will be x to the 3/4. Now, there's kind of a common understanding here that when you start with radicals, your answer should finish with radicals. So we should write this as the fourth root of x cubed. If we started with fractional exponents, we'd finish with fractional exponents. It's just kind of, the answer should match the form that our problem is given to us in. On this next problem, we have a cube root and a fourth root being multiplied together. So we really have 5w to the 1/3 times 5w to the 1/4. Okay, well the 5w's are the same. Let's get a common denominator for these exponents. Let's put them each over 12. So we would have 5w to the 4/12 times 5w to the 3/12. Adding those exponents together, we have 5w to the 7/12, and we can rewrite that in radical form as the 12th root of 5w to the 7th, and I will write that as 5 to the 7th w to the 7th. When it comes to division, you're not allowed to divide a square root by a cube root, but again we can use our fractional exponents. We can write this numerator as u to the 3/2 and the denominator as u to the 1/3. And now we're going to subtract exponents, and we'll need a common denominator again. So I will have u to the 9/6 divided by u to the 3/6. Subtracting, that should be 2/6. Subtracting, we have u to the 7/6. Let's now write this in radical form, which would be the 6th root of u to the 7th. And since the power inside is larger than the index, we can bring a u out and have the 6th root of u left over. And I know this is a little tricky, but technically absolute values belong around that u on the outside, unless there is a disclaimer telling us that the variables represent positive values or non-negative values. Instead of treating this as a fourth root of 8, let's take that 8 and think of it as 2 times 2 times 2. Because now what we really have is the fourth root of 2 cubed times the square root of 3. Let's now write these using fractional exponents. I would have 2 to the 3/4 times 3 to the 1/2. I'd like these all to be under the same type of root, and so I would get a common denominator of 4. Let's go with 2 to the 3/4 times 3 to the 2/4. Now we can put these inside of a fourth root, have 2 to the 3rd times 3 to the 2nd, and inside that's really an 8 times 9, and we can simplify this further to the fourth root of 72.